So it's great to have Simon here. So I guess Simon doesn't need an introduction. He was an associate research professor here in the Robotics Institute. He was also a principal research scientist at Argo. And then he decided to move down under, and he's currently the director of the Australian Institute of Machine Learning. He also collected a lot of career awards. And today he will be talking about a very exciting topic, how to do learning with less. So let's welcome Simon, and Simon, please take it away.
Well, thank you so much, and it's really humbling to be here and amongst some new faces and some old friends. I'm here. And yeah, so today I'm, as I said, coming full circle and sort of coming back to give a bit of a talk to you guys. It's about learning with less, or for professors, it should be doing research with less, because it's sort of like we're always sort of resource constrained and not enough compute and all these other things. So I think it's something of high interest to many academics. So yeah, and as Lazo mentioned, I'm now at the University of Adelaide, and I'm director of the Australian Institute for Machine Learning. So, we've got a bunch of academic roles. We've just actually landed a brand new centre there. That's a $30 million centre, so we're hiring another 3-4 professors. And we actually got some alum from CMU that we've just hired recently. So if anyone's interested in those sorts of roles, please come and have a chat to me afterwards. There's a lot happening, and be very, very happy to talk. And there's some nice wine and sun there too, so that's the other thing too. Yeah, the wine helps. So today's talk, what are we talking about? So we are living in this age of big data, right? We are used to working with big data sets, lots of data, millions, perhaps billions of examples. And we are witnessing the revolution, and it's not revolution anymore, right? For those of you who are coming into grad school and coming into university now, it's just normal that I can ingest all these images, and I put it through this funny black box that I call a neural network. Graduate classes give you the recipes for how to do the neural network. No one really understands why it works or how it works, but it's this black box that's seemingly magical. I ingest all this data. I have the desired output. It could be a segmentation map, it could be flow, it could be object labels, and seemingly from this data, I can generalize to all my other examples coming through. And it is a modern miracle, all right? Sort of like top schools like CMU, MIT, big tech companies, they're all leveraging this. Now, as we know, one of the big things that hurt deep learning at its inception was we could see that lots of data would help, but it's going to be really hard to get all the labels, right? So this was one of the big issues when deep learning hit, like 2014, 2015. How do I get enough data with the labels? And so all these sorts of ideas came about. And fortunately, there's been a lot of progress on this. And the progress on this is basically reposing the problem as a bit of a reconstruction problem. So instead of actually trying to map from the input images to the labels, I actually asked the network to reconstruct itself, right? Or not, we asked the network to reconstruct the signal itself. So we can throw images in, the network spurs them around and reproduces them back out. But as we all know, neural networks are kind of like errant children, right? They're always looking for the shortcut. They're looking for the easy path out. So if you just do this, it's going to fail, because the neural networks say, I'll just do identity. I won't do anything to it. I'll just feed the image in, I get the image back out. So we need to make the network work. So we have this thing of like masking. Masking is becoming super popular, right? I just take big chunks of the image out, such that, and I ask the network to reconstruct it, and we call this self-supervision, but I can reconstruct it. And what's great now is I don't need any labels. I can just scale and scale and scale and scale. And we're living through this amazing period of sort of just scaling, where the race is on to whoever's got the biggest data set and the most amount of compute. So you're seeing people going around asking for like $7 trillion for compute, right? So like just crazy, crazy ideas. And it's not just images. We can do this exact same trick. And obviously, one of the better papers at CVPR that covers this, masked autoencoders, is a great example. But we're not just seeing this in image. We're seeing this in text too, right? So you can kind of like take text, take the words out, and this principle's almost identical. You just reconstruct, and you can literally ingest the entire internet and get very, very powerful networks that are then, you only then need a small amount of labeled data to train up the networks afterwards. So we're kind of living through this period, and this is all pretty normal for most of you guys in the room. You've taken classes on this. A lot of your research papers are on this. So BERT's probably a good example of that. And we're seeing this this exponential scaling. And so I love this plot, right? So this is sort of some of the recent LLM models that have come out. And on the x-axis, you've got years. So it's not in decades, it's years. On the y-axis, you've got the log scale of parameters. And just in like 5 years or so, you're seeing this exponential growth. And with the advent of GPT-4, you're sort of getting up to 1.8 trillion parameters, right? But what's interesting with this is that the recipe, the thing that goes into it, basically has stayed the same, right? So there's not really been any big innovation with the algorithms themselves. It's mostly the data and the compute. And so if you listen to your favorite podcasts on AI, people refer to this as emergence or scaling. And so a lot of people are, and a lot of VCs and big tech companies are sort of betting big on AI is kind of solved, and all I really need is lots of data and lots of compute. And you're seeing this being seen all over again, probably the most popular one at the moment, and this is sort of like, I think all of us, everyone's jaw dropped when this landed, right? Sora. So like this amazing thing of just putting a bit of text in, and you get this amazing sort of scene back. Again, just leaning on lots of data and lots of text. Although, we had a fun thing. When it first dropped, I went with my kids, and first off, we were amazed, but then we were doing a sort of a Where's Waldo game of sort of looking for the mistakes. I don't know if you guys did the same too. So even in this one, there's a mistake. If you keep looking at her legs, there's some periods where the legs rotate. They actually they're walking like this, and then all of a sudden, they switch, right? So they're kind of like, even then, there are little mistakes coming in there. But again, a lot of people are saying just enough data and enough compute, and those problems will go away. So is AI just big data and big compute? And if it is, what the hell are you all doing here, right? You might as well just sort of like go out, buy lots of computers, lots of data. We know the answers, and scale everything up, right? And this is sort of the idea that we're sort of witnessing at the moment. Now, and there's actually a great, I don't know how many of you guys have seen this blog. It's called The Bitter Lesson by Rick Sutton. Some people have seen it, yep. So, and it's basically this idea that a lot of the stuff that we're doing in AI at the moment is just sort of fiddling around the edges. And really, if you just hold on long enough and you have enough data, enough compute, that's the thing that's going to really matter. So, is that it? Well, I'm not sure if that is it. And for those of you who don't know me, I used to be a professor here. I was a professor here for about 12 years. And for about 5 years, I worked in the autonomous car industry. So I worked at Argo AI for a number of years. And it was a lot of fun. We learned a lot. There was a lot of hype around autonomous cars around 2017. Everyone believed that it was going to be solved in 2 or 3 years. It was a lot harder than we thought. But what was really interesting with the autonomous car problem, like many robotics problems, is that it requires a lot of perception, right? You've got a vehicle, you've got a ring camera, and in real time, you're having to detect all sorts of objects, vehicles, things moving around, trying to detect where things are. And seemingly, this is a problem that's ripe for scaling. Lots of data, lots of compute, and the problem should get easier and easier the more data that I collect. But there's one thing that sort of I realized as I was in the company, and we were actually deploying things, and I thought that there was a guy called Andrej Karpathy, who many people know used to be at Tesla, he's at OpenAI, and he's all around the place. He had a great tweet, and I thought it captured it well. So the tweet kind of basically said, real-world data distribution is N01, and good data set is U-22, right? So to most people, in the lay, they think we're speaking Klingon, right? But for CMU people, we all speak Python to each other, so we're very, very comfortable sort of talking like this. But I'm going to visualize what Andrej sort of meant by this. So what he kind of meant, and it's sort of captured here. This is sort of an awful image. I hate this image, right? It's a small child walking onto the street. Something that hopefully in your years of driving you'll never run into. You might have like an autonomous car driving, and it may never run into this for years and years and years, right? Now, fortunately, this child was fine. Everything was fine with this child. But what Andrej's tweet was sort of capturing was that this instance is extremely rare. Never happens. I could be collecting terabytes, perhaps petabytes of data, and I might not run into many instances of that. Whereas things like stop signs Very, very common, especially here in Pittsburgh. And so what Andre was sort of talking about is the distribution that an AI needs to do well, current AI needs to do well, looks like this. Everything needs to be equally likely, right? And so the data that we train on is not the data that we need when we're actually deploying systems, right? So there's a complete mismatch. And to me, if you want to sum up the big challenge in AI and computer vision at the moment, it's this. It is this fundamental mismatch. So a lot of the work that we do at the institute that I direct is fundamentally directed at this problem, right? Because this is where AI fails at the moment, right? And there's all sorts of people of different ideas. If you look at NVIDIA, NVIDIA's tried to simulate their way through this problem. They're trying to basically simulate the world so they can then attack the tail, right? And a lot of different people are hitting this in different ways. But fundamentally, this is the problem, this mismatch between the data we need to train on versus the data we can capture. So, and we see this in other areas, right? So GPT-4. GPT-4 is like this amazing thing. And those of you who went to CVPR, there's a great keynote there by Yenjin Choi from UW. And she was just playing with GPT-4 and showing how amazing it was, but also where it fails. So she had a great example where you just ask it to multiply numbers together, right? And many of you guys have probably seen this. And you ask it to multiply two numbers together, and it gives you an answer that looks, to the naked eye, looks pretty good. It's wrong, right? GPT-4 gets multiplication wrong. And so what's really interesting, this highlights the example again, 3-digit by 3-digit, 59% accuracy, 4-digit by 4-digit, 4% accuracy, 5-digit by 5-digit, 0. More and more rare. The more and more rare the instance is, right, and the harder it is for the system to do. So, and again, if you haven't captured the paper, great paper by Yenjin Choi. And a lot of the problems that we face in robotics are really these extreme problems. I might have a submarine being deployed into the deepest depths of the ocean, encountering areas I've never seen before. I can't simulate, I can't see it beforehand. How do I get my algorithm to work? It could be in a conflict area, right? I've got maps of big cities. I don't know what the map's going to look like after a conflict. Robots going into sort of, again, sort of dangerous areas, or even detecting rare types of cancers. This problem comes up again and again. So what do we do? Now, what's interesting is we humans are narcissistic. We kind of tend to look at ourselves for all signs of intelligence. And so when we look at humans, humans aren't quite like neural networks. We are actually quite data efficient in our learning, right? So we don't need nearly as many examples to get similar types of performance. And so the big question of the day is, how do I fix that gap, right? Is it simulation? Is it sort of causal reasoning? And one thing I've become really interested in is something called neural priors. Something here, all right, that sticks to it. And what it's talking about, typically when we think about neural networks are just vehicles for reflecting back data to us, right? It's just a way of sort of like smoothing data out and just basically using it back. But a neural prior is something different. A neural prior taps into the implicit bias that we see in modern deep networks. And perhaps that alone could actually be useful. Not the data, but the architectures themselves. And I'm going to try to convince you through this talk why it's interesting. So what is a neural prior? What does Simon mean by a neural prior? Well, typically, other than data, there are three considerations that you have when you're training a neural network. The first consideration you have is the architecture, right? How deep? What activations? Whether I do batch norm, whether I have skip connections, do I do a transformer network? So the choice on the architecture. The second thing we take into account is the optimization method, right? It's sad to say that for a lot of young people, right, optimization, when you say optimization, they say, oh, you mean SGD? You go, no. There are other types of optimization out there. Gauss-Newton, LBFGS, people are using a lot of Atom. But the type of optimization that you use actually brings an inherent bias to your neural network. And finally, initialization. Initialization is almost never discussed in any neural network class. Maybe you might do a little bit of thing on climbing he initialization, or you just say just randomly initialize, but after that, it's just put to bed, right? And even when you use PyTorch, you never touch it. You just basically initialize your neural network, form your neural network, and the initialization is done under the hood. You never even look at it when it goes on. And one thing that's really interesting is some of the work that we've been doing is we can actually show that you can switch these things out. I can get a certain type of performance with an architecture, but if I change the initialization, I can completely change the performance or optimization and trade off between the three. And they all bring an inductive bias to the neural network. So when you're poor on data, thinking about these three forces is really, really important. And there's a lot of important work that needs to still be done to understand fully how they interconnect. Okay? So, and I think we make a big mistake a lot of the times when we just choose one. I see a lot of papers, they just talk about architecture. A lot of papers, they just talk about optimization. All three interplay and play together. So let's start with architecture and give me some examples. So in architectures, I typically have my example again of images. I'm masking parts of the image out. I've got an encoder and decoder. And so, but one of the problems with these types of networks, right, is that once I do the training and I deploy them at runtime, the networks are frozen, right? We have this idea that all the optimization should be done before I go out, right? So no more optimization, just freeze it down, right? And it's great because it runs fast, but the big impetus then is getting lots and lots of data, and the network's frozen. And one of the problems there, right, is that there's no mechanism for feedback. And so because of that then, I have to collect huge amounts of data just to get the thing to work well. Now, before neural networks, it was very popular in computer vision to actually solve optimization problems in real time. So we have a very famous computer vision professor here, Takeo Kanade. He actually pioneered a lot of the work in there. So optical flow, Lucas Kanade, all these things, these were runtime optimizations. You would solve the optimization problem at runtime. It was never frozen. So people have been exploring a little bit about the idea of solving neural networks at runtime, not freezing them. And so the idea is sort of, it's interesting. So one of the, I think, more notable efforts in this was this idea of you'd have a single image, not a big data set, a single image. Take some patches out of the image, right? So it's hidden. Have a random code and just a decoder. And then you just ask the question, my code's random, I'm not learning it. What's the decoder that can reconstruct the image? Right? And it's a crazy idea, but it was actually an idea put forward by Andrea Vidaldi at Oxford in 2018. He called it deep image prior. And the idea is really interesting because when you go do that, you run this, it's not a big data set, one image. You go run this, and you go and train your network. You actually get a natural feedback mechanism on the missing data. And actually, when you go and deploy it, and you can try this yourself, you actually reconstruct the image in full. There's no data coming in. Now, obviously, you can be really aggressive, like take too much of the image out and it will fail. And I've exaggerated it here, but if you take chunks of the signal out, it will actually interpolate and recover them. And that's actually coming from the natural inductive bias in the network, not from the data. And again, when I first read this paper, I was sort of in disbelief. I didn't believe it. I didn't think, nah, he's making it up. There's something weird going on. It's called deep image prior. There's been some follow-on work. Hands up here, who's heard of NERF? All right, everyone's put a yeah. So NERF is basically this idea. It is this idea, okay? Except you substitute your random code for coordinates. You fix the coordinate, you have a decoder network that's taking as the input the coordinates, and you're asking to reconstruct an incomplete signal. Right? So if you think about the radiance field, you've got this radiance field you're shooting rays through. You never get all the rays, you only get a subset of them. And the neural network somehow magically fills in the rest. How does it fill in the rest? It's the neural prior. It's filling in, it's interpolating those missing parts. So, and you guys know it well. You don't have to apply it to NERF. You can apply it to any coordinate. I've got X and Y. I concatenate them all together, and I get my RGB value. And so essentially, at runtime, again, a single image. I'm not running this in a billion images. The single images, I run them over the coordinates, train the network, and then I can actually reconstruct the missing signal. And so there's this whole field emerging at the moment on representing signals as deep networks. So historically, we've always used neural networks in computer vision to transform signals. But there's this whole field, it's like signal processing for neural networks. We're using them to represent signals. And so it's really powerful with this idea. So I've got my coordinates, I've got my neural network, and I'm mapping to my image. And it trains on coordinates. It reconstructs, not transforms the signal. And oftentimes people refer to these as implicit neural functions. Like, I'm sure you've heard this. I'm using an implicit neural function for this. I'm using an implicit neural function for that. My lab, we call them coordinate networks, because I hate implicit neural functions, because most of the time, there's no implicit function, right? It's sort of a ridiculous name that people have just used. It's from graphics, and I don't know why we still use it. So I like coordinate network, because that's really what it is. We've got some here. And again, radiance fields are probably the best example. I won't get into this example too much. And obviously, radiance fields are amazing. You can get depth images. We've seen radiance fields being applied at city scale, like block nerf. Obviously, there's a bit of a battle going on at the moment. Gaussian splatting seems to be winning. So this talk's not about radiance fields per se, but it's just sort of talking about the implicit bias that you get from these neural networks. Now, when you try to represent a signal as a neural network, there's something really interesting. All the stuff that you learnt in your computer vision class, if you took computer vision with me, everything I taught you is wrong. Most of the time it's wrong anyway. But it's wrong because we basically go into class and we say, well, deep networks are better than shallow networks. The best activation to use is ReLU. You should use SGD. We don't offer you guys much intuitive reasoning or mathematical proofs in it. We just say, look at all the papers. The results are good. This is why. What I love about implicit neural functions is when you apply this to these types of signals, all those rules fail. So if I take a deep network on coordinates and try to reconstruct an image, something really odd happens. So I'm just going to let it train, go through it. And it doesn't matter how deep you make it, how much samples you make for it, you cannot get a good reconstruction of the signal. There is an inductive bias, something that smooths the signal out. And you can try this out. I actually have some class notes up from some tutorials I teach. You can play with some of the Colab examples here. The classical deep ReLU networks fail for reconstructing signals. Now, if you're an engineer, you're frustrated and you look for a hack. But if you're a computer scientist, you kind of go, why? That's really weird. This is like a problem where deep ReLU networks actually fail. They don't do well here. So the hack that got put forward in NERF, and I do call it a bit of a hack, right? It works really well, is basically they said, well, let's not use ReLU first off. Let's use sinusoid activations. And let's just randomly initialize the weights, all right? Now, most of you can say, well, that's really weird. Hands up, who's heard of positional encoding? Okay. That is positional encoding. Positional encoding is essentially a neural network with random weights and sinusoid activations. We don't talk about it that way, but that's all they really are. Like, there's variants on it. The most common positional encoder is something called random Fourier features. And so that's essentially what they are. They're randomly weights with sinusoids, and away you go. And there's a bit of a hand-wavy explanation of why that helps, but we're going to get into it in a bit more detail. But it actually adds bandwidth to the network, okay? So you are stuck with ReLUs. ReLUs have a very, very low bandwidth bias, okay? So for classification in high-dimensional spaces, that's really, really good. But for representing low-dimensional signals, it's bad. So you actually need to have activations with higher bandwidth. And sinusoids are really, really good for that. So, and that was really, really intrinsic in getting NERF to work. It's an important hack, otherwise it fails. So, but positional encoding by itself is bad, right? And there's been some papers done by this. Probably the most notable papers are by a guy called Vincent Sitzman, who's an assistant professor at MIT. We've done a little bit of work together on things. And what he showed, right, is if you get an image that's reconstructed using sinusoids with ReLU, you get really noisy gradients. Okay, so the image looks right, but if you just do a Sobel filter on the image, you get these noisy gradients. And the second order gradients are awful, right? So if you want to do something classical like Lucas Canade, it will fail because you have no good gradient information, okay? So you're destroying that. So Sitzman put forward is that it's a bad idea to use ReLU at all. So what he put forward is that you should have a deep network just with sinusoids, all right? And you shouldn't randomly initialize them, you should learn them. And again, the intuition here is that you want to be able to control the bandwidth of the signal. If you are confused by what I mean by bandwidth, if you've done signal processing, bandwidth is the number of frequencies, how high your frequencies can go up to, so the width of the frequencies you can reconstruct. And so Sitzman showed that this was sort of a good solution. And it's called, often people call it about Siren. It's an ICCV 2021 paper, very, very interesting. But Siren has some issues too. So Siren is really sensitive to initialization. So if you go through the details of the paper, Siren sort of noted that we can get it to work, but we have to have this very, very special initialization to make it work. And without it, you get sort of this type of behavior. It just sort of gets stuck. So now, one thing, if you've studied signal processing, you may or may not know, is that if I have a Fourier sequence here, up to a certain bandwidth, I can apply a transformation to it. Okay? I can make a transformation to it, an orthonormal transformation to it, such that they're spatially localized. And what that spatially localized transformation looks like is a sinc function. And the sinc function, the width of the sinc function, dictates the bandwidth of the reconstruction. So the wider the sinc function, the lower the bandwidth. The more narrow the sinc function, the better the bandwidth. So back in 2022, we were ideating over, why use sinusoids? Because if you're initializing, you could get they go on forever. You could get all sorts of issues with initialization. Why not use sinc functions? Sinc functions are localized, and so they're much better to initialize with. And a great approximation to sinc functions are Gaussians. So basically the width, your bandwidth then, is just the variance of the Gaussian. So we put forward something called a deep Gaussian neural network. And so the idea is that it's basically a deep network with Gaussian activations. But what's really cool is that you can do run-of-the-mill initialization, just sort of the regular stuff you use in PyTorch, and it works. And you can control the bandwidth. No positional encoding, nothing. And so we actually had a paper it was an oral at ECSV 2022. It's called Beyond Periodicity. And we have a whole theoretical treatment over what activations you should and should not use. Again, if anyone's doing implicit neural functions, stop using positional encoding with ReLU. I will reject your paper. It's just nuts. So we have, and then we put forward something called Gaussian activated radiance fields, which is basically a version of NeRF just using these things. And the advantage of it is that you could solve problems. So I had a paper back in 21 with Antonio Tarabla called BAF, which was NeRF with bundle adjustment. And so the idea was that you had to try to kind of align. You could do this with images, you could do this with NeRF. But one of the advantages of GAF is with this, you had to do this really messy course define on the positional encoding and all this messy stuff. Here, this just works. No special initialization, no nothing. And actually gets state-of-the-art results. So, and we also showed it sort of like reconstructing radiance fields. So we can get the radiance field and the cameras all at once. So typically in NeRF, you need to have the cameras calibrated. You run a cold map or something beforehand. Here we're solving for both at the same time. And we get much better depth maps and images back out too. GAF again, some images back out there. Yes?
When you said you were going to calibrate the cameras as well, do you know the intrinsics?
And I have the...
My problem is hard.
and this is why it's always good to have Srinivas in the room, because he calls me out. The extrinsics. I'm doing nothing with intrinsics, and you're spot on. And it's a dangerous term too. When I said calibration, you're spot on. That is implied there. So it's the extrinsics of the cameras, not the intrinsics. So the other application for this, beyond NeRF, is hands up who's heard of physics-informed neural networks? A couple of people? This is really big now, especially in areas of science. So people call them pins, right? And so the whole idea here is, again, it's really interesting. I might have a field I want to reconstruct. It could be electromagnetic field. It could be Navier-Stokes, fluid flow. It could be a high-dimensional field, just like a radiance field. Radiance field is a field, right? But oftentimes with these types of problems, I only have a sparse set of measurements, maybe only a couple of them. But I know the physics of the problem. So what I can do, and I sometimes refer to these as sort of virtual particles, I can get virtual measurements here. I don't know the measurement of the field, but I know the physics, and I can enforce the physics here, right? And so what's amazing, it's basically an implicit neural network with this extra physics prior added to it. And what's amazing is people are using it for determining heart flow. Like you can get heart flow, you're doing things on fluid flow, electromagnetic, a lot of stuff in physics at the moment are using pins at the moment. So it's basically Nerf for physics. And it's really, really popular at the moment. And so we've actually also applied some of our ideas there. Again, in pins, everyone's using ReLU or 10H. And the results are sort of so-so because there's a big inductive bias there. So, and this, if you've not seen this paper, it's been cited like almost like 10,000 times now. It's massive, massive. And this is one example of a paper that you should think about as students. It's a great paper because it's a problem that leans to machine learning but cuts across all these different areas of science, and people are just using it. And so we also explored this. We actually explored the different activations. And again, Gaussian activations have these really nice properties. They converge quickly. They solve. This was something we're doing Berger's equation here, but you can do Navier-Stokes, and I've got an archive paper here what goes into that. So if you're doing implicit neural functions, check out these activations because there are much better ways to do some of these things. The other thing that we look at is optimization. So again, in neural networks, we love doing SGD or maybe ADAM. One of the reasons we love doing this is if I take a regular deep ReLU network and I apply ADAM, there is no real benefit of using a second-order solver. So a common second-order solver in PyTorch is something called LBFGS. If you don't know what that is, just remember high school physics or high school math. It's basically a Newton method. You're taking second-order gradients. When you're using ReLU, there's no real benefit. There's no gap to this at all. All right? And we're taught this over and over again. First-order solvers do not help with deep networks. Really? Potentially, that has a lot to do with the activation. So ReLU, which has a really, really heavy implicit bias, doesn't benefit from a second-order solver. But if you've got activations that have higher bandwidth, you can get a big gap over there. So we've been actually doing things with Gaussian-activated deep networks, and second-order solvers really help. And it turns out that if you're applying them to things like Nerf, you can get big speed gains by just switching the solver, given that you match it to the activation. Again, thinking about the architecture and the optimization at the same time. Two things at the same time. The other example that we have is I worked for the autonomous car company Argo for a couple of years. And one thing they were really interested in was LiDAR, like a lot of work on LiDAR. In robotics, we do a lot of work on LiDAR. And so one of the problems that they really were interested in was something called scene flow. And so one of the ways of doing scene flow is you maybe have a LiDAR point sweep at time t, and another LiDAR point sweep from t plus 1, and you want to work out the flow, how those points move. Okay? Now typically, because LiDAR is sparse, they're not in correspondence. So instead of minimizing the corresponding error, we minimize something called chamfer distance, which is sort of this proxy for the two. Right? And typically, and so what we proposed back in 21, one of my PhD students, Zhuxuan Li, who actually did her master's here, she followed me over to Australia, she proposed this neat idea where we regularize the flow, not with a classical regularizer, we regularize the flow with a neural network. We say the flow is represented as a neural network. It's not trained on anything. The only thing we do is we choose the architecture to give the inductive bias. And what's really interesting, in the 3 years since it's been published, it's basically state-of-the-art. In all the benchmarks that are used in scene flow at the moment, neural scene flow prior is probably one of the best benchmarks that are used at the moment. It's trained on no data. It's like really surprising, right? And it scales up, and it's just the choice of the architecture that helps. So that's an example there. And what you can see it in action. You get the sparse LiDAR points here. You can fuse frames together to densify them. There's scene flow. I've got the scene flow, and I can bring them all back into the same canonical frame to densify it. But you can also do some other interesting things too. One of the problems with the runtime optimization is that it can be slow, right? The immediate question is that if I'm going to do scene flow on a car, I can't wait around 2 hours for the neural network to solve the flow. So we've actually had some work recently at ICCV 23 where we have a really fast version of this. And we take advantage of some classical ideas like distance transforms and other things like that. But what's really powerful with it is with our new approach, here you've got the time for the network to run. Here you've got accuracy. So you can see the orange blocks here, they're feed-forward neural networks. Really fast, but the error is bad. Here, you've got neural scene flow prior. The error is good, but it's really slow. So last year, we published this new technique. It's just as fast as a feed-forward network. It's running a runtime optimization in real time. But we have actually better accuracy. And you can actually see this in action here. You can actually see in the traffic flow, and all it's doing is getting the scene flow between these parts. Right? You can actually densify these parts. And what's really interesting, it's not just about densifying things. We actually have a paper at CVPR 24, and Jenny, who is not here, but she's one of L'Oreal Tachet's students and is visiting Deva at the moment. She was working with me and Laura on a new paper that's at this CVPR. It's called What Moves Together Belongs Together. If you check it out when you come to CVPR, but what we're doing is we're using neural scene flow prior to detect brand new objects, just using motion cues. No training data. We're not saying that's a car, that's an elephant, that's a person. It's just motion. Okay? And so what's really cool with it is that you can scale up with large amounts of data. So check it out if you get a chance. Finally, initialization. Okay? So I've spoken about architecture optimization, initialization. So with initialization, we ran this really cool experiment. So I made the mistake or the fortunate decision to actually hire 2 mathematicians when I moved to Australia. No background in computer vision or AI whatsoever, but they'd done a lot of stuff on like knot theory and other things, so they can talk math that I can't even understand. But they were fascinated with the problem of why do deep networks generalize? They're really interested in this. And so they came up with a really nice thought experiment. So they said that, let's say I've got, and coordinate networks are a great way to play with some of these ideas. So let's say I've got these samples. X is my input coordinate, okay, sampling here. Y is my training data, or my training labels, right? So I've got this sparse thing. And to the common eye, right, we can see that this is sort of a sinusoid. It's just sampled really sparsely. So I actually run these networks, these points, through a neural network. And what I can do is I can kind of see what happens, right? What I can see is that, and this is what we're showing here. It's a little bit odd. What we show is before I train the neural network, I'm going to show the Fourier transform of the signal of the neural network. And so, and what I mean by this, and I probably should have visualized this, if you get a coordinate network, say one-dimensional input, one-dimensional output, randomly initialized in PyTorch, and you can set the random initialization to whatever you want, you will always get out a smooth curve. Doesn't matter what you do, you will always get a smooth curve out. So if you do the Fourier transform of that curve, you will get a low frequency response and no high frequency parts. And so then when you go and train on those little dots that I was showing before, I get a pulse of the frequency that you see there, but nothing else. And so Hemant and Lachlan then asked the question, is this from the inductive bias of the ReLU network? So they did another question, and obviously you get a really good result out. It's nice and smooth, and you get that back out. They then did another experiment. So instead of randomly initializing your network, like we're always taught, they did what I'm calling at the moment a structured initialization. You say, what is a signal that I want my neural network to predict? Perhaps it's a high frequency pulse, okay? So I generate a high frequency pulse, train my network on that first, right? And if you do the Fourier transform of that, you actually see this high frequency piece here. I take that network. That is my initialized network, okay? That's what I'm using as my initialized network. And then I train on the sparse data. And what you see is the same pulse on the training data, but the high frequency pulse remains. Right? I'm just going to let that hang. Optimization's the same. Architecture's the same. The only thing that changes is the initialization. Now what's interesting is I get perfect train error. Train error is perfect, but the generalization error is catastrophic. And this flies in the face of everything I've been taught in deep learning. So when you go and visualize that, you get the perfect responses, but in between, no smoothness. And this is ReLU, right? It should be a low frequency bias. But just by choosing the wrong initialization, I can break it. So what's also really interesting is that you don't have to do this just in 1D. We tried this idea on CIFAR. So we actually go and say, all right, let's go to CIFAR and train a CNN up and do a low bandwidth initialization. And that's typically the standard one we do, just randomly initialize the weights. And when I go do that, I get 100% train accuracy, That's what we'd expect. And that's analogous to me fitting those points, right? But what I care about is the unseen points. When I go and do that, I get a test accuracy of 86% on the low bandwidth. But we also worked out a way to do a high bandwidth initialization. And I can get into how we did that, but we worked out a way to kind of initialize at high bandwidth. And when I went and did that, I still get 100% train accuracy. Train accuracy is perfect. 49%. It's a deep ReLU network. CNN, everything else is the same except the initialization. My train error stays exactly the same. And I can break the generalization properties of a deep network just by changing the initialization. Weird, right? And it actually, it violates everything I taught in 16720B. I said, this is why this works in 16. This is not what I was teaching. The other thing that's weird too, and we applied this across a bunch of networks. So ResNet, ConvMixer, we have some transformer networks in the latest, but the paper's called How You Start Matters for Generalization. It was at ICML last year. And we also have a new paper out, because all the rage in computer vision at the moment are VITs, right? Everyone wants to use VITs. But VITs are a pain in the butt if you're a student, because you need to train on large amounts of data. If you want to get a VIT to train well on small amounts of data, then you really need to pre-initialize with a large amounts of data beforehand. So we basically explored this idea where if you do a traditional initialization with VIT on small data, like CFAR, you get bad results, like 59%. But we have this new approach that we're calling structured initialization. And you can find details of it here in this archive paper. And by using structured initialization without any extra data, we can go up to 77%. Again, balancing these two things. The initialization matters. It matters when you're initializing.
Question.
Yes?
You know what the distribution of the data is on the test side. I could create a test set that matches the distribution of whatever the top network is doing, and I might get a better test accuracy. So I'm not understanding how the
So we're
the connection.
So the magic here. So in this one there is, I'm glossing over some of the details here, but going back to the original part, what we're doing is we're sort of making this argument that when you do a regular initialization of a deep network, there is a low frequency bias that comes in. So it automatically smooths things. And so,
Why is that wrong is what I'm trying to understand.
it's actually not wrong, but sometimes for some types of, well, it turns out for VITs, it's really bad. Because if there's a part of a VIT called self-attention, and you randomly initialize that, it's trying to work out how parts of the tokens should be swapped together. And we know things about images, right? Certain patches should be closer together than other patches. You can bake that in. And so we've got this convolutional initialization. So we kind of play with that a bit. But coming back to the original question, it is not bad to have that smooth assumption. But one of the things that it's really problematic, say with NERF and other things, you want to break that. And the other thing I think that's really interesting is that people never looked at the initialization as the reason why these neural networks generalize. And I'll just to follow up on what you're saying there, the next slide sort of gives some clarity on this. This is a CVPR paper at 2024. It's one of our assistant professors. It's not my paper, but they kind of used some of our work. What they explored was different types of deep networks for different activations. And they wanted to work out what the frequency responses were. Okay? So ReLU, GLU, 10H, and Gaussian. And on the y-axis, they randomly initialize, and they just basically play with, what if I scale the weights up and down? What happens to the output signal if I do an FFT on it? And what happens with ReLU, this is the amazing thing with ReLU, it doesn't matter how much you scale the weights or how deep it goes, it's always low frequency, which kind of explains why when you classify images and other things, you get such great generalization performance. It always smooths. But if you use a different activation, a Gaussian, it's terrible, which explains why you should never use Gaussian activations for image classification. Right? Because if you go too deep or randomly initialize, you start actually aliasing. You start actually filling in and getting noise in there. And so if you're doing a high dimensional problem, use ReLU. But if you're doing low dimensional problems like NERF or implicit neural functions, You want things with higher bandwidth. So change those activations. And there's a real, and they have analysis on transformer networks in here. It's a really good paper. If you haven't checked it out, it's just up now. It's on CVPR 2024. So to conclude, it's an open problem on how architecture, optimization, and initialization relate to data efficient learning. Better understanding of coordinate networks will lead to better insights for deep learning in general. And I liken coordinate networks a bit to like in physics. Like in physics, people understood everything at the macro level, but it took us going down to quantum to work out where classical methods break. I really like implicit neural functions because they're the same thing. We understand how to use neural networks on big, high-dimensional problems, but in low-dimensional problems, what we've been taught breaks. And what I really find fascinating is when something breaks, we can better understand why it works and hopefully make better networks. And then finally, a whole new field is developing around coordinate networks in the application to discovery of physics. And that's one thing I haven't touched upon. Potentially, you could use some of these things to discover new types of physics, new types of constraints, because you could perhaps try to work out, you could think about different types of physics like Maxwell's equations or Navier-Stokes. They're essentially just linear classifiers applied to fields. And you can think about how I could learn different types of physics. So it's really interesting. A lot of people are exploring this at the moment. And then finally, we're just starting to understand how to interleave runtime optimization with offline learning. So anyway, thank you very much. Happy to hear questions. Cheers.
So we have time for a couple of questions.
Yeah, thank you for the presentation. A small question about your AIML 2023 paper. Is it because something you did wrong with the Narcissist sampling theory that because you artificially created
Very good. So for those of you, and it's surprising, a lot of people aren't taking signal processing anymore. So a lot of young students don't even know what Nyquist is, right? So if you don't know what Nyquist is, hopefully you do. If you see the old time movies, right, you have these things that you have like a wheel moving by, and if you get the frame rate right, it starts going backwards the wrong way because you're sampling at the wrong rate, right? That's one way exactly to think about what's happening with your activation. You want to choose the activation so you don't violate Nyquist. And ReLU is really powerful because it guarantees, irrespective of how deep or how large the magnitudes of the weights are, you won't violate Nyquist because it just basically makes sure it's low bandwidth. Whereas, and so this partially perhaps explains also why in the early days of neural networks, we weren't seeing the generalization. A lot of people kind of argue it's because we didn't have the compute. We didn't train it for long enough, which I think is true. But ReLU has some really, really remarkable properties with respect to low bandwidth. And it's in tolerance. So it's not invariant, but it's very, very tolerant to changes in depth and also changes in weights. And that makes it really powerful. I think, and partially, and that's one of the things that they speak about in the paper beforehand, another reason why deep ReLU networks, and the same argument applies for your favorite activation, GLU, anything that kind of looks like this, right? It really doesn't matter whether you do this or whatever, right? It has the same spectral properties, and people like these things, right? But they all have the same principles.
Scale equivalent to the
exactly.
Word.
It's I'm trying to think of the word. I can't think of the word, but you're exactly right. Like if I go ReLU sigma x, it's the same as ReLU x sigma, right? I can always take the 2 out of there. Most activations don't allow that. ReLU and a small other sets allow that. And it's that property that gives it the invariance. Exactly, yeah. Yeah, so check out the paper. Yeah, not my paper, that's why I'm advertising it. But one of my professors, he did it. Yes?
What are your thoughts on the hash encodings and how do they compare against what you talked about?
Oh, yeah, that's cool. That's something that we haven't got into. I mean, and that's that's the danger of this too a little bit because there's been so much done in neural networks, so many activations out there. So that's something we haven't investigated. I think that's something that we need to look into. And I guess sort of like what I like about this line of inquiry, it's sort of like I think we have other papers that are cool and other things, but what I like about it, it's just getting students to challenge what we've always been taught, right? So go deep, go ReLU, do standard initialization, and everything else is everywhere else. Whereas I think for some problems, really thinking about that. And so we haven't explored that, but it's a really good question.
So yeah, thanks for a great talk. So you had this very nice slide in the introduction where you had the human learning performance and the machine learning performance chart. So I think 2 questions on that. One, are you sure the human curve should be above and not necessarily the point? But maybe the second one is you thought that we should view this talk as trying to bridge that gap, and you like these trials will help us do this more efficiently. But to me, that implies that we are all agreeing that that is the way, and we have to get some details right, as opposed to we need another revolution in machine learning to actually learn.
And this is a really fair question, right? So I think to reflect back your question, right? I think one of the criticisms of the idea of neural priors is that in some ways we're going back to the dark days, right? So the dark days in terms of a lot of heuristics, a lot of changing things. We're not using data to guide how to design things. We're just sort of choosing and things. And I think some of that work can be accused of that. I guess one thing I wanted to kind of say was that we are already kind of doing that unwittingly. So that was just one message there already, right? So it's not that sort of, and I think just to kind of push against this narrative that neural networks are just reflections of the data. So that's one point. I do think for some of the problems that we're encountering, right, we do need a different way, a different paradigm. And I'm not saying neural priors are necessarily the only way forward. I like it because from my time here at CMU working with some of the brilliant people here, good ways forward always come from asking questions about when things break. And so that's basically what this talk is about, where things break. I don't know if neural priors are necessarily the only way forward, but it is good to be cognizant of sort of what's happening and what's going on. The thing I am a bit bullish on, but is structured initialization. I do think that I am really curious, and this is one thing we're working on, how much of transformer networks are spent getting the right type of initialization in attention. And if you could bake that in, how much data you could save. So that's one thing, and we've actually been playing with that a little bit. And the other part that I like too is if you have an understanding of what you need to do, we have a paper at this 3DV where we showed how you could take in PointNet, if you guys are familiar with PointNet, used for 3D classification things, if you take out a lot of the learning parts and replace them with high bandwidth activations, you can actually do a really good job with no learning. And so we can actually challenge the question of sort of how much of PointNet really needs to be learnt. And so we actually kind of, so we have a paper there, and we do this with point cloud transformers too. So yeah, but it's a really good question, and I totally hear you, because I'm not advocating a going back to the bad old days. I'm just saying that we're not necessarily sitting in the good old days we think we are. Yes, Fernando.
Thank you very much for this very clear and enthusiastic talk. You've been always a big fan of linear algebra and linear systems. There are ways, approximate ways to approximate neural networks with neural tangent kernels.
Yeah.
So if you have infinite bandwidth, these systems can behave as a kernel.
Yeah.
You know. And I was wondering if you have found any connection, or if you have explored this connection to try to explain the behavior of this activity.
Yeah, so it's a really good question. So for those of you who don't know what Fernando's talking about, like NTK kernels are a tool used by a lot of theoretical machine learning people to analyze like what's happening. And so people kind of apply the kernels, and then they can apply sort of these classical methods. You can look at the kernel matrix and look at what's sort of going on. So a lot of people with coordinate networks, ourselves included, almost to get these papers through now, you need to do sort of NTK analysis. And so we do that and kind of put those parts through. I think NTK is a great tool. I don't think it's everything, but it's a fantastic tool for kind of like piercing inside what's happening. I do think that there is a connection, right? So like if you do sort of the SVD on the NTK kernel, you can actually also see sort of some of these inductive biases that are coming in, and you can kind of draw those connections as well. But yeah, so that is something, and in some of our treatment, we do explore that. I don't know. You're more mathy than I am. So my mathematicians that are in my group, they love NTK, and so I push against them some ways because I think sometimes it hides the intuition, but I think it's a really, really good tool. Yeah, you'd probably do better than I would on that. Yeah. Yes?
So I guess I'm curious how you decide when you're looking at a problem whether you want the like low bandwidth properties of the ReLU or the high bandwidth properties of like a Gaussian
It's a really cool, and how do you live in between? So like that's the other thing too. So answer to that is that it's kind of the curse of dimensionality. It's something that we used to get taught in the 90s and the 2000s, right? So it's a reason why nearest neighbor classifiers don't work above a certain size. I guess one of the things we find is that if you've got a low dimensional problem, and we were kind of playing with this a bit, my rule of thumb is anything below 5 dimensions, you should be using a high bandwidth activation. All right, so if it's like a radiance field or any field like that, you should probably be doing that. What's interesting too is that there's been so many papers that have come out is when someone uses a deep network in a low dimensional space, they nearly, a year later, there's always a paper that comes out that essentially uses a shallow network and does exactly the same thing. So if you guys were watching NERF, there's a follow-up paper about a year later called planoxyls, which you look at it, it's essentially a shallow network on the problem. And so I think that's an interesting question, where you should use those activations, but also where do I need deepness? And so I have a bit of a running bet with one of my postdocs at the moment. My bet is that whenever you need a high activation bandwidth, you could almost always get away with a shallow network giving you the same performance. And it's a bet that we've got going at the moment, whereas deepness, there's no way. So for high dimensional problems, like for image classification, text, all these sorts of things, you want those low frequency properties. Yeah, sorry?
Where would you put seed flow in that space? Because like on the fast update, for example, you're using ReLU, right?
Yeah.
On that coordinate.
Yeah, and, all right, so someone knows the work really, really well. And so in neural seam flow prior, we do use ReLU. And so one of the reasons that we want is because we really want it smooth. But in our follow-up work, we actually kind of pushed away from some of those activations. But yeah, that's it. And so if you what you want in the problem, that's something that they can help. But say for image reconstruction, or if you've got scene flow where you've got big changes and other things like that, that really, really matters. Yeah, really, really good question. Take care.
It wasn't clear to me your initial description that the world problem is not Gaussian, but this uniform.
Yeah.
See, if you are still evaluating the performance by average, the data that available,
They should match.
then the number that you get is biased by this the data that was collected with this probability, not this one.
You are totally correct. So like what Takeo is saying is that, well, Simon, you're saying it's a bad thing to have the train data distribution match the test data distribution, and you're exactly right, because if they're matched, you're going to get better test error and other things like that. But the issue is if you have that outlier, like if you're running a big company and you're showing that you get all these low error rates, but then you deploy your cars and the car runs over a child, that one rare, your stock value goes.
Most important.
Exactly. Yeah. So it's important sampling, right? So there are some samples that are way more important than others, and it tends to be the samples that are the furthest away from the training distribution. They're the things that will cost you the most as a company, and I think that's one of the issues.
The second question is that after all, the success of the neural net is relying on smoothness of the world, or a little more generally, some structuredness which we may not know.
Exactly.
But the biggest of that is, of course, the smoothness. And if that's the case, then I wonder how, say, for example, your 3D flow is doing better than Euler integration, which is Euler integration is relying on simple continuity of the function, right?
Yes. Yeah.
Whereas your network must have captured some kind of a structured smoothness of the world.
Exactly.
So in that sense, the pictures, which we tend to call illusion, or the scene that tend to give a wrong impression that one of the famous one that I learned is somewhere in Canada, there is a called magnetic hill,
Oh, yeah.
which appears to be going upward, but it's actually going downward.
Yes, yeah.
So that kind of a scene which gives a problem to human, and we call it illusion.
Yeah.
Which probably, if we are working in the same way, then those scenes are violating the structure or smoothness that I learned,
Yep.
or you learned.
Yep.
How your network or neural network in general responds to
It's
those
a really,
scenes.
and this is always the thing. Takeo always asks the best questions. It's a really, yeah. So you're right, and that's one of the questions that we're trying to ask ourselves at the moment. How much of this is sort of like that the priors that we're seeing in these neural networks reflect the priors that we see in the real world, or how many of them sort of violate that? And we're still not really sure on that, but to go to your point with scene flow itself is really interesting because it's really popular at the moment in implicit functions to have these things called space-time networks where you do X, Y, Z, and T going in. And so what's really interesting, right, is in those types of networks, you perhaps want X, Y, and Z to be smooth, but you want to have really high bandwidth in time. And so it's a bit of an open question at the moment. It's really easy to design these implicit neural functions when I have equal bandwidth properties across all the dimensions. But if I have one, and this is one thing we're looking at the moment, if I have one mode that has different bandwidth, how do I bake that in? And so, and that's sort of like, again, to your kind of point a bit, if I know something about one thing, how can I bake that in? And I think that's where, I guess the only kind of message I'm trying to kind of give across in this talk here is that we as humans know a lot about the world. We are potentially baking into these neural networks things about the world that we don't realize. And if we're aware of it, if the things change or you're an engineer, you can do that without having to go and collect a lot of data, or at least understand why things are breaking. And so, yeah, but it's a really good question, yeah. Oh, all right, yes.
Another question about, say, yeah, do you think if prior would be something opposite to now the trend of say rely on massive data, right? Sometimes prior is harmful.
Yeah, so this is, I think that sort of like, if you have enough capacity in your network and enough data, you can always overcome the prior, like if you train for long enough and in other parts. But I think sort of like when we do image classification, right? Even when we have lots of images, just the sheer size, if you visualize like these images as points in high dimensional space, they're just so massive that you always have that issue. So there's always that prior part definitely coming in. But it is an issue too. Sort of like saying, and I think that's what's amazing with deep networks, with ReLU, right? Is that if you don't have a lot of data, it's got this low frequency bias the entire time. And so it will always smooth out things. But then if you have enough data, it has the capacity to fill things out. Whereas when we used to learn shallow networks, back when I was younger and I was here at CMU, there used to be this awful trade-off. We had this trade-off with basically that I could have less capacity, better generalization, or more capacity and actually worse generalization. And part of it comes down to this bandwidth issue. So when I added capacity, I'd initialize and have horrible properties there. So I'd hallucinate things. And I think that's part of the magic of deep networks, that they can maintain that low frequency bias even with the capacity. That's my intuition.